Hello, welcome to this lesson on photons. To start with, we'll quickly go over some points relating to waves, wavelength, frequency and speed, and talk briefly about electromagnetic waves. Then we'll be ready to talk about photons, and also talk about the term wave-particle duality. We'll then move on to photon energy and the Planck constant. That will take us to calculations we can do, so you will need pen, paper and calculator to try the problems for yourself. Let's start by talking about waves. Now I hope you've already met waves at an introductory level, so this should be a little reminder. Let's suppose you drop pebbles into a pond, one after the other. You'll see waves spreading outwards, like a snapshot of the waves. The blue rings are the crests of the waves, the high points on the water. The grey rings are the troughs, the low points on the water, and the pattern spreads outwards, and as you drop pebbles in, more and more rings appear and spread outwards. This pattern of waves, it's got a definite wavelength. If you measure the distance from the centre of one crest to the centre of the next crest, that distance is called the wavelength. It's given the symbol lambda, which is a Greek letter. The wave travels at a certain speed. If you followed a point on one of the crests as it travels outwards, you could measure the speed. We'll give it the symbol v. If someone was on the left, say, watching the water, they could count how many crests pass them per second as the crest moves towards them. Or they could count how many times the water goes up and down each second. It's the same thing. That's the frequency, the number of vibrations or number of waves per second. And all waves have a frequency, wavelength and speed. And these three quantities are related by a simple formula. The wave speed is frequency times wavelength. Of course, we've got to get the units right in SI units. V is in meters per second, F is in hertz, and wavelength is in meters. Let's talk briefly about electromagnetic waves, sometimes called electromagnetic radiation, and sometimes electromagnetic is abbreviated to EM. Here's a list. I wonder if you can recognize it. There's some more things to be added to the list. What should be added? If you want to pause and think about that, you can do it now. Well, I hope you know ultraviolet, X-rays and gamma rays to be added. This list is called the electromagnetic spectrum, and it's a list of all the different sorts of electromagnetic waves in order. In this case, the order is increasing frequency. The waves with the lowest frequency are called radio waves, and the waves with the highest frequency are called gamma rays. Or we can think about it in terms of wavelength. The waves with the longest wavelength, the long waves are called radio waves. It can be many meters long. And the ones with the shortest wavelength are called gamma rays, tiny wavelengths. You ought to know the rough values of some of the wavelengths. Radio waves, many meters. Visible light, many exam boards expect you to know this. So there's the colours of the rainbow. Red is about 700 nanometers wavelength, and as you go through to violet, the wavelength gets smaller. Violet is only about 400 nanometers wavelength. So that's the electromagnetic spectrum. We haven't yet said what electromagnetic waves are, though. We know what water waves are roughly, we just talked about them. What are electromagnetic waves? Well, for water waves, it's the height of water that's changing. For electromagnetic waves, nothing's actually moving. The electromagnetic waves consist of rapidly changing electric and magnetic fields. Now, if you don't really know what electric and magnetic fields are yet, don't worry, I hope you'll learn about them later on, but it's worth noting they can exist in a vacuum, in empty space. So these fields can exist in empty space, and the pattern of them moving along can. So all of these electromagnetic waves can travel through empty space, travel through a vacuum. And a key point is that all these waves travel, or propagate to use a posh word, at the same speed in the vacuum. Radio waves travel just as fast as gamma rays. Their wavelength is long, but their frequency is low. Gamma rays, their wavelength is small, but their frequency is high. And it turns out they travel at the same speed in the vacuum. And this speed is very important. The speed they travel is called the speed of light. In fact, it should really be called the speed of electromagnetic waves, but we call it the speed of light. So gamma rays travel at the speed of light. And the symbol we use for this is a small letter c, and the speed of light is about 3 × 10⁸ meters per second. Actually slightly less, but that's usually accurate enough for most purposes. It's a universal constant of nature, the speed of light. Another key point about electromagnetic waves is they all carry energy. Okay, that's enough background. Let's start talking about photons. First of all, though, let's go back to the wave picture we had earlier on for water and see if we can apply it to electromagnetic waves. Let's imagine in the middle we've got a radio transmitter sending out radio waves. So these blue rings now represent regions where the electric and magnetic fields are very strong. And this pattern spreads outwards. Thinking of electromagnetic radiation in terms of waves like this is called the wave model of electromagnetic radiation, and it basically is saying that the waves are a continuous stream of energy carried in the moving patterns of electric and magnetic fields. It's continuous because these rings are smoothly expanding outwards, carrying energy smoothly. Well, about 1900, physicists realized that electromagnetic radiation didn't always behave like waves. Sometimes it behaved more like lots and lots of tiny particles of energy. And that's called the particle model of electromagnetic radiation. And it says that rather than the electromagnetic radiation being waves spreading out like this, the electromagnetic radiation is really a stream of discrete, that means separate or individual, a stream of discrete packets of energy called photons, almost like little particles of energy, lots and lots of them. Each is called a photon. Let's draw a diagram to try and represent that. So instead of thinking of our radio transmitter sending out waves, we can think of it firing out billions upon billions of tiny particles of energy each second. Many photons being produced and emitted each second. Each photon separate from all the other photons. Not wave-like at all. And you can do experiments to show that electromagnetic radiation behaves as waves, and you can do experiments to show it behaves as these tiny packets of energy. When you learn about the photoelectric effect and quantum mechanics, you'll learn more about this. But for the moment, it's enough to know that both views of electromagnetic radiation are valid. And because photons, these little packets of energy, are particle-like in the sense that they're separate from one another, we say electromagnetic radiation exhibits, which means shows, wave-particle duality. That means sometimes it behaves like a wave, sometimes it behaves like these little particles of energy, these photons. It can behave both ways. Dual means two. So we call the fact it can behave both ways wave-particle duality. And when you learn quantum mechanics, you'll learn more about that. You'll learn that even things we think of as particles, like electrons, can also sometimes behave as waves. But that's out of the scope of the present lesson. We need to talk more about photons. First thing is nice and simple. The symbol we use for photons in some equations is a gamma. That's a Greek letter gamma. And it doesn't just mean a gamma ray photon, it can be used for any sort of photon. If we're drawing diagrams and want to show photons, we usually draw a section of a wave with an arrow sticking at one end, showing the direction. What can we say about photons? Well, fairly obviously, I hope, they travel at the speed of light, c. A photon has no mass. To be technically correct, we should say zero or no rest mass. Rest mass of something is its mass when it's not moving. While a photon is always moving, it can't stop. It always travels at the speed of light. And scientists argue about whether photons have got mass or not. As far as we're concerned, a photon has no mass. That's a nice simple statement. A photon has got no mass. It's also got no charge, not positive or negative, it's neutral. Please don't do what some students do, which is mix up photons with protons. A proton is a positively charged particle found in the nucleus, not the same thing at all as a photon. Each photon carries what's actually made of some energy, and we call that energy the photon energy, the energy which is in a single photon. That's the photon energy. We're going to be talking a lot about this. And finally, let's just note a photon is usually described as a packet of energy, or it might be better to say a packet of electromagnetic energy. It's a separate entity, it's a packet, self-contained packet of energy. The energy in a photon, we've mentioned, is called the photon energy. We give it the symbol E. E is the energy in a single photon. We're going to be using that. Let's move forwards. We know what E means, the energy in a single photon. The physics now starts. Photon energy is proportional to the frequency of the wave. Let's suppose we have our radio transmitter sending out a signal. We can think of it as a wave with a certain frequency or loads of photons. If we double the frequency, we find the energy in each photon is also doubled. The energy, the photon energy, is proportional to the frequency of the wave. Let's write that symbolically. E is proportional to F. Now, I hope you know we can turn proportionalities into equations by replacing proportional with equal constant. So we can say E equals constant times frequency. That's a very important equation for working out the photon energy if you know the frequency. And we'll have this constant, we give the symbol H. And the constant is very important. H is called the Planck constant, or some people call it Planck's constant. Its value, it's a universal constant, like the speed of light is a universal constant. H is 6.63 times 10 to the minus 34 joule seconds approximately. Things to note, it's a very small number. 10 to the minus 34 makes it very, very small. The other thing to note is the units. It's not joules per second, it's joules times seconds, joule seconds. And it's important because it relates the wave model, which is a frequency, to the particle model, which has a photon energy. So it links the wave-particle duality models of electromagnetic radiation. It links particles to waves, H. And let's just talk about this formula briefly. We know what H is. E, of course, must be in units of joules, and F must be in units of hertz if we're working in the SI system of units. A little warning, in some books you may find the symbol nu. That's a Greek letter nu, which looks like a V but isn't. It's a Greek letter nu. Sometimes a Greek letter nu is used for frequency. So you may, instead of seeing E equals HF, you may see E equals H nu. Okay, I've done enough talking. It's time for you to pause the video, read through this and have a go. Do that now. Pause the video now. Well, I hope you've had a go. Let's go through it. First of all, it's a straightforward application of the equation. if you're writing this down, make your working clear. So you write equals HF. You substitute the value for H. The value for F is 100 megahertz. It's got to be in hertz. So we replace M by 10 to the 6. Mega, capital M, means a million, 10 to the power 6. So the frequency in hertz is 100 times 10 to the 6. You don't really need a calculator for that. It's 6.63, 10 to the minus 26 joules. Don't forget to put the unit at the end, of course. For the second question, well, let's rearrange our formula. F is E over H. Put the numbers in. We know what E is, given that in the question. Divide it by H. Round the answer to 3 significant figures to match the data. And 1.96, 10 to the 14 hertz. That's a pretty high frequency. Let's move on. There's our formula. Sometimes you're given the wavelength and you have to work out the photon energy. What do you do then? Well, we know for an electromagnetic wave, the speed is the frequency times the wavelength, true for all waves, and for electromagnetic wave, we use c for the speed of light. So that's a key formula for electromagnetic waves. Now what we could do, if we were given the wavelength, we could use this formula to work out the frequency, and then put frequency into the top formula. Gives photon energy. But there's a neater way. Let's just recap what this formula requires. C is the speed of light, 310 to the 8. F is the frequency of the wave in hertz, and lambda is the wavelength in meters. That's the key formula. So here's an exercise for you. Which of the following formulae, plural, is correct? You may want to pause the video and decide which of those 4 is correct. And I hope you tried that. Number 4 is correct. Let's make sure we can see how we got it. We know C is F lambda. Let's rearrange that to make F the subject. So F is C divided by lambda. We know equals HF. So let's replace F by C over lambda, which is the same as F. So we end up with E is H times C over lambda, which is the formula number 4. So we end up with 2, actually. Very nice little formula, useful. E is HF. If you know the frequency, that's good. E is HC over lambda. If you know the wavelength, that's a handy formula. I'm going to use that in a moment. But before we do, the next questions, 2 more questions to go. Here's a preparatory exercise for you. Let's suppose a laser has a power output of 100 watts. How many joules of energy does it emit per second? If you want to pause the video, you can. Well, I hope you realise the answer is simply 100. 100 joules per second. The reason is 1 watt, which is a unit of power, actually means a joule each second, a joule per second. 2 watts means 2 joules each second. 100 watts means 100 joules each second. So a laser with a power output of 100 watts is producing 100 joules of energy each second. Next question. Let's just suppose that each photon emitted by the laser has an energy of 25 joules. That's a ridiculously large amount, but it makes the method easier to understand. Let's suppose each photon carries 25 joules, and the question for you is, how many photons are emitted per second from the laser? Pause, think about it. I hope you realise it's 4. Why is it 4? It's because each second, if there's 4 photons produced, 4 photons will carry away 25 joules each. So we're carrying away 4 lots of 25, 100 joules of energy each second. Do you see what we did? We saw how many 25s there were in 100. So the general method, if you want to know the number of photons emitted per second, is this. We divided the power in watts by the energy in a single photon in joules. So I divided 100 watts by 25 joules, divided by the power, which is the energy per second, by the energy in 1 photon. Remember that, because we're going to use that in the next exercise. If you didn't follow that, pause the video, read through the screen, make sure you've got it clear in your own mind. Okay, question 3. You can read that for yourself and have a go. So pause the video now. Well, I hope you've had a go. Let's go through the answer. For part A, let's use the formula E is hc over lambda. We know what h is, put the number in. We know what c is. We're going to divide it by the wavelength. We've got to have it in meters. 633 nanometers. Nano means 10 to the minus 9. So the value we divide by is 633 times 10 to the minus 9. That's the wavelength in meters. And if you do that, 3.14 10 to the minus 19 joules. Give the answer to 3 significant figures to match the data. What about part B? Well, I hope you remember what we just said. If you want the number of photons per second, you divide the power in watts by the photon energy in joules. In our example, it was 100 watts and 25 joules. Here the numbers are a bit messier. The power in watts, 50 milliwatts, is 50 times 10 to the minus 3 watts, because milli means 10 to the minus 3, a thousandth. We divide that by the photon energy, which we've just worked out, and that gives us 1.59 times 10 to the 17. That's the number of photons per second coming out of the laser. Okay, one more question and we are done. This involves a unit you may or may not have met before, an electron volt, symbol small e capital V. It's called the electron volt. All you need to know for this question is that 1 electron volt is a special small unit of energy. It's equal to 1.6 times 10 to the minus 19 joules. So your questions are, what's the photon energy in joules and what's the wavelength in nanometers? Again, pause and have a go for yourself. Okay, well I hope you've had a go. Let's go through the working. 1 electron volt is 1.6 times 10 to the minus 19 joules. 2 electron volts is twice that. If we've got a photon with this amount of energy, 8.07 electron volts, the energy in the photon is 8.07 times 1.6 times 10 to the minus 19 joules. It comes to 1.291 times 10 to the minus 18 joules. Should really round that to 3 significant figures because the data supplied is 3 significant figures. So that's the photon energy converted into joules. For the next bit, we want the wavelength. Well, if we take our formula E is hc over lambda, we can rearrange it to get lambda is hc over E. Stick the numbers in, h times c, divided by, let's use the unrounded 1.291 10 to the minus 18 value for E. It's got to be in joules. We can't use the value in electron volts, we use the value in joules. Do the numbers, 1.55 10 to the minus 7 meters. But if you remember, the question said in nanometers. How do we convert meters to nanometers? We multiply by 10 to the power 9. So I've got a typo there. It's 155 or 154, I don't know which. But multiply by 10 to the 9 and we get 154, perhaps it's 155 nanometers as the final answer. Okay, there's a lot to take in. It's rather a long lesson, but thank you for watching.